There are multiple regression models. Okay, we're going to just get a couple of different ones, specifically from chapter 6. So we're going to look at a exponential model, a logarithmic model, and then what's called a logistic growth model. Okay, so we're going to look at a couple of really specific models here. First of which is going to look at an exponential. Now, for the video for 4.3, I went through how to use Desmos to do all of this. So largely what you're going to find in this video is mostly just the answers to the slides. Just kind of a reminder of these are the models you use in, this is how you type them in, this is what your screen should look like, sort of a thing. Okay, so this video will be probably unnaturally short, but same thing as 4.3. Take the time, go to Desmos, type this stuff in, make sure that it's working for you. Make sure that you can get your Desmos to show the same things that mine is showing. Without that, you're going to get really, really messed up when you try to do the homework for these. Okay. Now, again, just like 4.3 and the intro to stats stuff, you do not have to show work for these questions. You don't have to turn in that PDF to Canvas, but you do need to do the homework. Okay. And the homework is going to be in your Desmos app, and if you can't work the Desmos app, then you're going to struggle with the homework, right? So make sure that you can do these, go type it in, go make sure it's working. If it's not, email me, come to office hours, see the tutor, whatever it is, and come up with how this is going to work for you. Okay. All right, so I've got a table up here, put it in, I've got my models down here. Now, just like I told you before, there is no R value. This is nonlinear, so the R value does not exist. Well, it does not apply. Okay? Instead, we use something called R squared. And it's a slightly different measurement. It's calculated in a different way, but it gives us about the same information. Okay? For this particular set of data, R squared is 0.9974. It's going to be pretty close to 1. Now, there are no negative R squareds. Okay, but you're still looking at close to 1 or close to 0. This is pretty close to 1. It's a pretty good model. We can say it's a good model. It's what we would expect it to be, or what we would want it to be. Okay. Once you have these models, then you can kind of decide what to do with them, and that's just going to depend on the question that is being asked of you. So in this case, it's saying, use Desmos exponential regression to fit your model. So that's what this purple line is. We've got the model. It's fit over the top of our data, so we can kind of tell what's what, where's where. Okay. Then it says, after 6 drinks, a person weighing 160 pounds will have a blood alcohol of about 0.16. How many more times likely is this person to crash if they drive? Okay. Our BAC is used as our X value here. Our risk is used as our Y value. So we're going to say X equals 0.16, okay, which is down here on this third line. And then over here where they intersect, okay, gives us our answer. So this is our blood alcohol content, and this is our risk. So at a blood alcohol content of 0.16, if that person chooses to drive, they are almost 30 times more likely to get into an accident than someone who is sober. Okay, that's what those numbers are telling us. Okay? They are 30 times more likely to be in an accident. Okay? Put it in Desmos, punch the numbers in, make sure yours looks like this. If it does, go to the next one. If it doesn't, send me an email, send me a screenshot. Let's figure out what's going on. Okay? All right, logarithmic growth. So same idea, except now I'm going to use a logarithm. Now, when you use Desmos, we only ever use natural log. Okay, we're not going to use like a log base 2, log base 22, it doesn't matter. We're just going to use natural logs. Okay. Now, since the last time I made these slides and published them, the model has changed. Every time, and it's only this model, it happens every time Desmos does an update, they change how this one works. Okay, so don't use this logarithmic model in the slides. You're going to want to instead use this one, okay, where you have to add in a horizontal shift to let the calculation be a little more accurate. Okay, I don't know why they do this to me. It changes. I have no control over when it changes. I don't know. Okay, so if it doesn't work, again, just email me and we will figure out what the new model needs to be in order for it to work. Okay, so again, we've got an r squared of 0.992. That's pretty confident. We've got our parameters in here if we need them. It's not asking me for parameters. Okay, so use Desmos, find a logarithmic regression to fit a model to the data. The question in this one says, use the data to determine how many games will sell in 2015. Okay, year is our X values, sales are our Y values. So we're going to type in a row, X is 2015, and we're going to come over here. All right, 2015 is our year, which means we're going to sell 170.56 games. I don't know why I wrote out the number again. Okay. Now we are past the data points, we're past our scatter plot. So again, this is going to be an example of extrapolation because of where we are in relation to the original data. Okay. Put it in Desmos, make sure it works, especially with the logarithmic model. Email me, send me a screenshot. If it doesn't work, then we'll get it figured out. Okay. All right. And then the next one is called logistic regression. Okay, there's no picture on this slide. It's fine. Okay, you don't. The idea of logistic regression. Oops, sorry. Apparently I got the wrong thing. Okay, is that there are models with what's called a carrying capacity. And what these models tend to do is, say I put 4 bacteria in a petri dish. At first, it has all of this space and it starts growing exponentially. It starts really shooting up there. And then eventually, after it grows for a while, it starts to realize it's running out of space and it's going to top out. Okay, it can only grow to the walls of the petri dish. And so we get to a point where, this is our top, this is where we end up. And it's a combination, right? From about here over is an exponential function. And from about here over, the same point to the right, this is more of a logarithmic. And so what we end up with is something called logistic growth, which is far more applicable to the real world, but is actually a combination of those two ideas. Okay. Now, here is your table. Go over to Desmos, put in your table. It goes from the year 1995 to the year 2012. So for space purposes, this table is kind of displayed funny, but imagine this side is kind of attached to the bottom of the left side. Okay, so you've got a big table, go put it in Desmos, and then we'll talk about these questions once you have them in there. Okay, so once you got it there, come back, we'll get it going. Okay, so you've got it in, we've typed in our logistic growth model. Okay, make sure that your y1 and your x1 match the y1 and x1 in the table so that you get a good curve. Okay, and then it's going to give us some parameters. So our parameters are down here. We have a C value, an A value, a B value. Now notice our A value is huge. okay, times 10 to the 225 means that I should actually move this decimal place 225 places to the right. Okay, so it's a massive number. Our b value, relatively small, right? 0.25, that's not too big. We don't need to know what those mean. What we need to know is what those numbers are and where they go in our model. Okay, the computer does that part for us. Okay, now use the model. Calculate the percentage of Americans with cell service in 2013. So we're going to go up here. This is our year. This is our percent. And so in 2013, we could say 99.34% of Americans have cell service, which is probably relatively accurate. I mean, you guys were alive then, so it seemed like almost everyone had a phone or had access to a phone. Okay. Now, the next one, just discuss the value returned for the upper limit C. What does this tell me about this model? Well, my upper limit is 105.74, and that's a percentage. Okay, does it make sense for 106% of Americans to have access to cell service? This isn't people with an actual cell phone in their pocket. This is people who are covered by cell service. Is it possible to cover 106% of the country? Well, not really. Okay, you either have service or you don't. So 106% of people having service doesn't make a lot of sense. Okay, that tells us that this model is pretty good, but probably not the most accurate model, right? It's pretty close. It's pretty close. If it was a perfect model, okay, in a perfect model, C should be 100, because I can only have 100% coverage or not, right? So in a perfect model, 100% of Americans have cell service and it stops. Okay, now that is part of what that model breakdown, right? When we talk about the model breakdown over and over and over again, it's not perfect because this model goes to 105. And so if I start making predictions too far outside of our model, too far beyond our data, well, eventually I'm going to end up with answers that don't make sense, right? 105% doesn't make sense. 102% doesn't make sense. So we just have to be careful, okay? That is what model breakdown is we are introducing error and kind of getting stuck in that error, okay? All right, those are the other three models that we're going to talk about just very briefly in this class. You'll probably see them again in stats once you take your stats class, but now you at least have a introduction to them and a model kind of idea that you can rely on and build upon once you get to stats, okay?